Good day, ladies and gentlemen. So this is chapter 11, which is about data structures. And this lecture, we're going to look mainly at a number of very well-known data structures, arrays, records, and linked lists. There are more, but these are the basic ones that we're going to look at. For this lecture, though, we are only going to look at arrays. So it's a very common data structure in any programming language. You will find arrays, basically the rest of the structures as well, but arrays is very often the most common and simplest data structure. So imagine you have 100 scores that we need to read in and maybe process them, print them out. Typically, like in class 151 situation, there's about 350 students. So basically, let's assume we have to read in a score, a practical mark, or whatever the case is. The example given here is just 100 of them. So one way we can do this is to keep these 100 scores in memory for the duration of the program. And to be able to remember them, we have to define variables to remember each of those scores, and typically it's going to be 100 of them. Each of them will have a different name. For example, the first score would be known maybe as score 1, the next one score 2, and so we continue until we get score 100. Another way to potentially remember this in the application that I just mentioned here is typically, for example, maybe the score of the student name. So score for Mr. Miller, or score for Mr. Buitendag, score for whatever. So in other words, there needs to be 100 of these variables where we could potentially enter a score like 22 or 55 or 98, which would be a very good score if it's out of 100. In other words, it's to be able to remember those scores. So, but having 100 different names is going to create some problems here. We need 100 references to read them. In other words, 100 variables. 100 references to process them. 100 references to write them to the screen, for example, if we want to write them out to the screen. So figure 11.2 shows a diagram that illustrates this problem. For example, we will need to do the following to successfully conduct this situation. If we want to read the 100 scores, we will start here. Then we will read the first score, the second score, and so we go on until we read the 100th score. Now we've read all 100 scores into memory, into the program, but now we must go along to go and process them. So then we must process score 1, whatever processing means at this stage. Maybe we want to process what the symbol is. So if it's between 90 and 100, or between 80 and 100, the symbol would be an A. If it's between 70 and 80, the symbol would be a B, or whatever. Alright, so then we do this processing on all 100, and then we will need to go and write the result out to the screen. So for example, if the result for the first score, let's say the score was 85, then basically an A would have to be written to the screen. And so we do this for every single one until we get to the last score. Alright, so you can see this is the basic thing that will have to happen in this kind of processing. Now, there's a better way to do this. Instead of having 100 different named variables, we can actually have an array. So an array is a sequenced collection of elements. So normally of the same data type. Now, although in some other programming languages we can have an array or a collection of elements with different data types, but for the purposes of this course and for the purposes mainly of any kind of array, we will teach in computer science to you that basically they must be of the same type. So we can refer to the elements in the array as the first element, the second element, the third element, and so on until the 100th element. So the way we refer to these elements is by actually talking about the name of the array. So the name of the array is called scores. So in other words, when we talk about scores, we literally talk about the entire array. And to refer to a specific score in this array of elements, we are going to do this usually by means of indicating the actual index. This is known as the index. So if we talk about scores 1, and by the way, the index, as you can see here, will be put between square brackets usually. So if we talk about scores 1, that's typically the first element. In other words, we are talking about this particular element here. Whatever is in there, maybe the value 22 is stored in here. Maybe the value 58 is stored in scores 2, and whatever, maybe the value 35 is stored in scores 100. So basically this is how, instead of having 100 separate variables with separate names, we have now one array with the name scores, and to access a particular element we use its index number here. Now we can use an efficient way to try and read through all the elements, and the way we're going to do that is with a loop. So you've already learned in chapter 9 about for loops and while loops, and we've even done it in an earlier chapter as well. So a loop we will use to read and write to the elements. We very often use a concept where we say that arrays and loops go together. Sometimes we say arrays are married to loops, which basically means that we literally will struggle, or we will do it very inefficiently, to refer to elements in an array if we don't use a loop. So loops and arrays go hand in hand. We can also use loops then to process the elements. We will look at examples in just a while. Now, it does not matter if there are actually 100, 1,000 or 10,000 elements to be processed. Loops are going to make it easy to handle all of them. So we can use an integer variable to control the loop. Sometimes we call this a control variable, and remain in the loop as long as the variable of this, the value of this variable is less than the total number of elements in the array. And we will see that in figure 11.4. So I've mentioned this actually on the previous slide, but we've used indexes to start from 1. Sometimes in modern programming languages like C, C++, and Java, we start indexing actually from 0. But for simplification reasons, in this example with arrays, we will start as the first element is element number 1 as well. But just take note that in future you might encounter, when literally looking at these languages, C, C++, and so on, Java, you will encounter the fact that the elements are being numbered from 0 rather than from 1. Right, so how will we process this array? By using loops. Well, here's a simple flow diagram that will help us. We're going to start over here, and then the first thing that must happen is that we need to initialize this control variable we talked about. So the control variable here, we're just going to simply name it I. So it's just a variable we create, and we initialize it to the value 1 because we want to start at the first element. And then we do a check over here. We check Is I less than or equal to 100? If that is the case, obviously because I started at 1 over there, it will be less than or equal to 100. It's less than, so in other words, it will start doing some processing. The well, so not processing as such as changing it, but the first kind of thing that will have to happen is that we will have to start reading the scores. So we will read score I. So if at first I was 1, we will read score 1. And because the next time we will have to read the next score, we must increment I. In other words, we must make I 1 more. So we're basically going to say I gets the value of I plus 1. So if I was 1 and we plus 1 to I will now get the value 2. And then we'll continue to the beginning of the loop and we will do our check again. If I is now 2, check. Is I less than or equal to 100? Yes, it is. Then we're going to continue with this loop, read score 2, and then add 1 to I, so I will now be 3. And so we continue and check, yes, 3 is still less than or equal to 100. And basically, we will continue in this loop until we find that actually I is now greater than 100, which means we should stop the loop and continue to the next part of the program, which basically then reinitializes I to 1. So we start I at 1 again, and here we check, is I less than or equal to 100? Yes, it will be, because we reset it over here to 1, and then we're going to do some processing. So whatever the processing is, as I said before, do some processing on scores I, and then again have to increase I with 1, so I becomes 2, and we go to the next iteration of the loop over here. Is 2 less than or equal to 100? Yes, it is, do processing, and so we continue until again I is larger than 100, which basically means then we will jump out of the loop, and the next thing we will do, we will yet again reinitialize I to 1 and check, is I less than 100? If it is, we will write score I to the screen, or score 1 will be written to the screen. I will be increased with 1, so I will be 2 now. We continue with this loop. Is 2 less than or equal to 100? Yes, and so we go on until this is not the case anymore, until I is larger than 100, which basically means we are done now and we can simply stop. So now let's look at what has happened here. Consider this example. This example 11.1 says compare the number of instructions needed to handle 100 individual elements as in figure 11.2 as comparing it with 100 elements as we've just done it in figure 11.4. Let's start with the first case here of figure 11.2. Processing individual variables. So in other words, how many instructions do we need? So in other words, if we use this process, we start, we read the first score, that is one instruction. We read the second score, that's another instruction. So how many instructions will we need to read the 100 scores? Obviously 100 instructions. And then we will continue with the next kind of instructions that will happen. We process score 1 and process score 2. So in other words, we'll need another 100 instructions to process all the scores. And then we continue here. Now we have to write each score to the screen. Each of those will be an instruction. Write score 1 as an instruction, score 2, score 3, up to score 100. So there again will be another 100 instructions. Shown basically in another way. So there we can see we read score 1, score 2, 3, 4, 5 until score 100. And process those 100 scores and write those 100 scores. Sorry for the spelling mistake over there, it should be an R. Write the scores. So just in total we see that basically we will read 100 scores, process 100 scores, write 100 scores. So it means we will have 300 instructions in this figure 11.2 if we have 100 different variables. Okay. Let's now compare it to 11.4. So again, just to refresh you, this is where we use loops. Let's see how many instructions we will have over here. So if we try to look at the number of instructions over here, then basically we with the loop fashion, we have an instruction here to initialize I to 1. We have an instruction here to check if I is less than or equal to 100. If so, read the score and increment I. So that's 4 instructions. And it goes into a loop, obviously. The next is the same, so for processing, you'll initialize I to 1 again, check if it's less than 100, process score I, and increment I. Same again for writing. Reinitialize I to 1, check if I is less than or equal to 100. If so, write the scores and increment I. So now if we have counted, it's basically 4 plus 4 plus 4. So there's actually just 12 instructions that we have to write in this program. Don't you agree that this is way less than the previous example where we actually had to go and write 300 different instructions? So you can see this way of figure 11.4 is way more efficient for us as a programmer, because it's using this concept of a loop here, another loop there, and another loop over there. So in summary for this solution, we see that in the first case, we need basically 300 instructions, and in the second case, we only need 12 instructions. So we can see 300 instructions versus 12 instructions. Clearly, the second case is actually better for us. We only need to write down 12 instructions instead of 300 different instructions. Let's look at the next example. So in this example, we are looking at the number of cycles. What is a cycle again? You'll recall from the early chapters, even from chapter 1, that a cycle, we actually mean that we need to do something here. A cycle, if you'll recall correctly, consists out of a fetch cycle, a decode cycle, and an execute, phase. A fetch phase, a decode phase, and an execute phase. Together, all of this constitutes what we call a cycle. Right. So remember, just for some revision, it's basically being able to read some data into the processor, decode that instruction basically to say, what do we need to do? Is this an add instruction, a subtract, or store, or whatever instruction, and then execute that instruction. And we can roughly say what we've done so far. Each line of code or each instruction that we had to write basically results into a cycle, an execution cycle. And that's what the computer needs to perform on that array. For example, we will need certain cycles to work through that array. But now, let us quickly see how many cycles we will need again if we look at figure 11.2. So 11.2, remember, it's where we have 100 different variables. score 1 up to score 100. And basically, if we have to read all of them, then basically it means that reading the first score is a cycle. Reading the second score is a cycle. The third, fourth, and up to 100, basically, we need 100 cycles to be able to read those scores. Then to do the processing, we need yet again another 100 cycles to do the processing. And to write those scores out to the screen, we yet again need 100 cycles to do that. So as you would have guessed from the previous example, from the common or the example where we had 100 different variables, we had to use 100 cycles for reading, 100 cycles for writing, for processing, and 100 cycles for writing to the screen, which resulted in a total of 300 cycles. We saw, though, that that was a lot of code we had to write. We literally had to write 300 lines of code. But if we look at figure 11.4, which seemed to have less lines of code, it doesn't necessarily mean that it has less cycles. How is this possible? Well, let's quickly see what's going on here. All right, so we can count the cycles when we start by initializing I as 1. That is 1 cycle. But basically, we're going to repeat in this loop, we're going to repeat 100 times. That means we're going to check 100 times if I is less than or equal to 100. So that's 100 cycles. We're going to check 100 times. In other words, we're going to read those scores. So that's going to be 100 cycles. And we're going to increase or increment I 100 times. So that's yet another 100 cycles. Right? And then for the next loop, we're going to reinitialize I, so that's a cycle. And for the same reason, we're going to have 100 cycles of checking whether I is less than or equal to 100, 100 cycles for processing, and 100 cycles for adding 1 to I. Similar to writing to the screen, we're going to reinitialize, so it's 1 cycle. We're going to check 100 times, is it less than or equal to 100? We're going to write 100 times. We're going to increase I 100 times. So now, if we're actually going to add all of this up, you'll see that's basically 301 plus 301 plus 301 cycles. So in the end, we end up with 903 cycles. That's almost 3 times more than in the case of figure 11.2, where we had several different variables. So now, what does this tell us? There's more processing going on in this way. All right, so let's look at the summary about what we came to learn now. So the number of cycles is actually increased when we use loops, because we have an extra overhead of doing some initialization of a variable, some incrementing of that control variable, some testing if the value is less than or equal to the index value. So the concern, as we said now, is with performance. However, with the PC that we know nowadays, we will easily handle those 100 elements or 300 or 900 cycles basically with no issue. But now what happens if we start to suddenly process 50 million items? You know, typically in South Africa we have about 50 million residents in the country. So what if we now have to write a process, you know, when we're doing census, and we maybe have to handle 50 million people's data? Okay, so if we had to handle this with figure 11.2, in other words, have 50 million different variables, or in other words, for that matter, have 50 million cycles, then handling 50 million cycles nowadays is actually not a problem. It can be done in a matter of minutes with the current processing power that we have. But writing 15 million lines of code, are you literally going to create 50 million different variables for each and every citizen in this country? If you have to type this, let's just optimistically say that you're going to take 3 seconds to type each line of code for each person, which is quite fast, and we, in other words, multiply that by 3 seconds for 50 million, it gives us 150 million seconds, and then if you go and do the calculations, you can go and do it yourself. We end up with typing 4 3/4 of a year, just typing this in. It's almost 5 years. So that's not efficient, as you can see. If we rather do it with figure 11.4, we will eventually then have 150 million cycles when doing those processing, but that will still be done in a matter of minutes nowadays with the processing power we have. And we saw that we can only do this with 12 lines of code, not 50 million lines of code. So by writing 12 lines of code, it's just going to take a few minutes. So a few minutes plus a few minutes is basically just going to cause us to do this in just a few minutes, because our concern is not here with the number of cycles. Our concern is with the number of lines as the programmer, for the programmer. So the programmer can write just a few lines in a few minutes, and we know, even though it's going to process 150 million cycles to do all the processing, it's okay, because the processors we have nowadays and programs we have can handle that in just a matter of minutes. And even if it will be a matter of hours, it's still much, much, much faster than, a matter of years. So hopefully I've convinced you now and shown you some of the differences between these two approaches. Let's look at the next example. This example says, in computer science, one of the big issues is reusability. Technically, I always tell my classes that, a computer scientist is typically a lazy person. Not really, but in terms of lazy, in terms of we want to do things fast and efficient. We don't want to spend so much time on doing things. We want to spend the quickest way in writing the program. So assume we have written 2 programs to process the scores, first based on figure 11.2, which would be those 50 million lines of code, and then later on we say writing 12 lines of code would be better for the programmer. So if the number of scores changes from 100 to 1,000 or even a million, how many changes do we need to make in each program? So in the first program, we would need to add 3 times 900, it's basically 2,700 instructions, if we assume 100 scores that we need to process. Obviously, it's going to be way more if it's 50 million. And then it's going to be 150 million lines of code we will need to change. But in the second program, as in figure 11.4, we only need to change 3 conditions. Every time where we check where I is larger than 100, now we're just going to have to change that to I is larger than 1,000, or in our example, I is larger than 50 million. So it's only those 3 instances. In fact, we can even reduce it to a single check. In other words, we can make the program a little bit more efficient than even 11.4. This is not in the textbook, but I've done it for you here to show you. This is just recalling 11.4. This is how we did it initially, in this way here. by having 1, 2, 3 checks here. And we saw that in the end we had to use 903 cycles for this. We can make this more efficient. We do it by reducing the code as follows. We still initialize I to 1, and then we check if I is less than or equal to 100. But we can do all of those things in this same loop. If that is the case, read the score, process the score, write the score, and increase I. And then we go and continue with the next iteration of the loop. Now let's look at the cycles we've used here. Now it's this one cycle, 100 cycles to check for I, 100 cycles to check for the scores, 100 to read the scores, 100 cycles to process the score, 100 cycles to write it, and 100 cycles to actually check or increment A. So in the end, we have now reduced it from 903 cycles to 503 cycles, as you can see in this example here. So what is making this more efficient is that we now only have, if we want to change that now to 50 million, we only have to do it once over there, not 3 times as in the original figure 11.4. Right, so let's continue with arrays. So the array name versus the element name, I already mentioned it quickly to you before. The array name in this case here was scores, and the element names, in other words, this first element here, that element name is scores1, or scores left square bracket 1 close square bracket. But if we talk about just scores, we talk about the entire array. That's the name of the array. When we talk about an individual element, we typically talk about scores1, for example, or scores2 for the second element, or scores5 for the fifth element, or scores100 for the 100th element. So the name of the array is the name of the whole structure, and the name of the element shows us to refer to that specific element alone. So as you've seen here, and as I've explained already in the figure here. Now we also get multi-dimensional arrays. In the previous example, the array we discussed was known as a one-dimensional array because the data in that array is organized linearly. In other words, into one direction. In other words, it is just a straight array of elements, starting from 1, ending at n. But you'll see later in computer science, in the courses that's still to follow, in your other courses, in the second semester, as well as in the later years, you will be confronted now with multi-dimensional arrays. In this course, we're only going to look at up to 2-dimensional arrays, but we later in computer science, you'll also start looking at 3-dimensional arrays and so forth. But in this course here, we're only going to look at 1- and 2-dimensional arrays. So what do we mean with a 2-dimensional array? Well, it basically is almost the concept of an array of arrays. So almost a 2-dimensional array can also be seen as an array of 1-dimensional arrays. In other words, typically if we just consider this, that would typically be considered just that, a 1-dimensional array, because that is an array with 1, 2, 3, 4 elements. Okay, but now we typically say that we have yet another array with 4 elements and another one with 4 elements, and basically in the end we have in this case an array with 1, 2, 3, 4, 5 rows and 1, 2, 3, 4 columns. And this is typically a 2-dimensional array The first dimension we typically refer to as the rows, these 5 rows, and the second dimension we typically refer to as the columns. So this particular element over here, if we want to refer to this element over here, we're going to refer to that element as scores 2, 3. Always the rows first, in other words, row 2, and then the columns, in other words, column 3. So in other words, row 2, column 3, it's basically that intersection of the row-column intersection, that element that we're referring to there. So, as another example, if this particular element here had the value 90 or 80, 85 in it, then basically this particular element is element scores 4, 2. So we will refer to that as scores row 4, column 2. All right. Let's continue. Now, in memory, things can be stored in various ways. Usually, the indexes in a one-dimensional array directly define the relative positions of the element in memory. So figure 11.6 below shows a two-dimensional array and how it is stored in memory using so-called row major or column major storage. Now this depends on how your system or the system is implemented. So usually most systems are implemented using row major storage. It hardly ever uses, systems are hardly ever implemented in column major, yet we're just going to show you the differences quickly so you see what we mean. So typically if we have this two-dimensional array over here, so logically the users see this two-dimensional array as an array with 2 rows and 4 columns. So data might be stored in the first row as A, B, C, and D, and maybe in the second row as E, F, G, and H. So that is typically in terms of row majors storage. That means in memory, remember in memory, we simply get a block, so to speak, of contiguous memory, and basically that block is divided up into rows and columns as well, and maybe it will start just there with A, B, C, D, and so forth, E, F, and so forth, and that's typically a row major. We start in rows first and then in columns. So you'll typically find that it is stored as A, B, C, D as the first row, and the second row E, F, G, H in this way. Or if it would consider column major storage, then basically instead of reading by rows, it's rather going to read first by columns. So then it's going to store the stuff as A, E, B, F, C, G, D, H. So there you can see in column format A, E, B, F, C, G, D, H. Alright. Alright, so this is not in the textbook. I just added this to try and explain it a little bit. Assume we have this whole thing, this whole yellow block over here. Assume that is the entire memory of the computer. So it's unrealistically small, but here we have basically 10 rows and 10 columns, which means we can store 100 elements in this, or 100 bytes in this memory. So the logical and physical memory positions differ. If we look at the user's view over there, you see this two-dimensional array with 2 rows and 4 columns in this case here. A, B, C, D, E, F, G, H in those rows. However, the place where it's stored in memory, you might find that it is stored like this, where A is stored over here, which is typically at memory position number, at physical memory position number 15. Column 5, row there. So in other words, if you would start over here, this block over here, this one over there, that's block 0. Block 1, 2, 3, 4, 5, 6, 7, 8, 9, and this one over here would be block 10, 11, 12, 13, 14. So this is physical block 15 in memory. So in the physical memory, you can see scores 1, 1. In other words, if we refer to that element there, we typically refer to it as row column. So scores 1, 1 is typically stored at physical memory position 15. Scores 1, 2, which would be that element over there, is stored at physical memory position 16. C will be at 17, D at 18, and so forth, up to 19, F at 20, G at 21, and H at physical block 22. Now, why it's stored in that fashion is because the operating system decides which part is, or will know which part of memory is free, and if you have to store this array, it will, let's assume that maybe this part of the memory was already filled up, and therefore it could only start storing it at that physical position number 15 over there, and that is why it would store it contiguously like that. But this is assuming we were using row major storage. Just to show you the same example, in column major storage is basically similar to this. Don't think that necessarily it's going to store everything now in a column fashion. It's still just going to store things physically in memory. It just means that the user view here, instead of first storing in rows first, then columns, it's now going to use column first and then rows. So in other words, the first element scores 1, 1, like this here, would be stored in physical position 15, as that's the very first one, because we now go column row first. So that's that one over there. So scores 1, 2 would now be that. In other words, column first, row second. That's now an E. That's why the E is now stored at physical position. Sorry, that's 16, not 17. All right. All right, and so we continue. So that one would be stored, the B would be stored at physical position number 17, and so forth. Okay, so that's just to show you, but this method is not really going to be used. We're going to assume row major storing unless I tell you something else. The next example. So in this example, it is also about finding out where physically something is stored in memory. So we have stored, let's assume we have stored the two-dimensional array students in memory. So the array is called students. The array, let's assume, consists out of 100 times 4, so 100 rows and 4 columns. Show the address of element students 5, 3, assuming that element students 1, 1 is stored in memory location with address 1000. So we assume it starts at position, or is stored at physical position 1000, and each element occupies only one memory location. So we must make sure about that. So in other words, we assume it each element consumes only 1 byte. The computer uses row major storage, so we also make that assumption. So where exactly is students 5.3 stored? So we can use the following formula to find the location of the element, assuming each element occupies only 1 memory location. Remember, it was given to us there, only 1 memory location. We can use this formula over here. So where we're going to say X is basically the starting position, or the physical starting position, which is 1000 given to us, with I rows and J columns. And then basically we just use this formula to say the target element occupies the location Y equals columns, which is now 1000, plus 4 columns, because the number of columns is 4, multiply by I is now 5, because we are in row 5, minus 1, plus the columns J, which is 3 at this stage, minus 1. If we just go and work out the maths to this, we will find out that students 5.3 is stored at physical position number 1018. So operations on arrays. So although we can apply the conventional operations defined for each element, like doing addition and subtraction and things like that, like we've done in chapter 4, there are some operations that we can define on an array as a data structure. So we can do conventional operations like in a one-dimensional array. We can try and add 2 scores together. So if we want to add score 2 to score 14, in other words, let's assume this particular array is stored here, and there's the entire array starting here at physical position number 15 in memory. So that will be known as score 1. Okay, and we assume this is the one-dimensional case. Later now we will get to the two-dimensional case, but now let's focus on the one-dimensional case in the left-hand array here. So that is just a one-dimensional array starting. The first element is 45, the second element is 91, the third element is 0, and so there's 20 elements, so the 20th element is 31, for example. So if we now say score 2 plus score 15, then basically this is score 1, then this is score 2 over here. And where would score 14 be? Well, there's score 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So basically we would say that score 2 plus score 14, that would simply mean 91 plus 96. We wanted to add those two together for some reason. In the two-dimensional case, I have just now, to make it easy for us, formatted the array here as a two-dimensional array also in memory, but it's not necessarily going to be this case, okay? Just to make things easy. So in the two-dimensional case, when we talk about scores 1, 1, which element do we talk about? Logically, remember this is the first row, in other words row 1, 2, 3, 4 and 5, and column 1, 2, 3 and 4. So if we talk about score 1, 1, row 1, column 1, we're talking about that score. If we talk about scores 3, 4, row 3, column 4, and that's the intersection, we're talking about that score. So in this case, we would be adding 22 to 74. All right. So that's just to show you some examples here. So the common operations on arrays as structures are also, apart from adding things and subtracting things and so forth, we can also search for a certain value in an array. We can try and insert a value or delete a value from the array. We can retrieve a value, in other words, just read it. Or we can traverse an array, which just simply means we're just reading through the entire array from the start to the end. That's what traversing the array means. Now, although searching, retrieval, and traversal of an array is an easy job, because, searching for an element, retrieving an element, or traversing through the array doesn't do any structural change to the array. You're simply just reading through the array. But insertion and deletion of an element, those things causes a structural change in the array. That's more difficult to do. To prove it, let's just look at an example here where we typically going to, in the first example, search for something, and the second example, we're going to delete something from an array. So the first example, searching, let's search for the element with a content of 32. So we must see if we can find 32 in this following one-dimensional array that you can see over here. All right, so we will start at the first element there and see, is this 32? And then we will continue to the next element, and so we continue until we find an element that has the value of 32, which we will eventually find over there, as you can see. So this is 1, 2, 3, 4, 5, 6, 7. We'll find it at the 8th element. So typically, the programming code we will use for this operation to search for a value is like follows. We first initialize I to 1 because we want to start at element number 1. I is our loop control variable at this stage. So then we use our loop, a while loop, and we say while I is less than or equal to 20, because we know there are 20 elements in this array. That's why we check, is I less than or equal to 20? If that's so, then we check, is this score I, so if I is 1, we're talking about that element, is score 1, which is 45 in the first case, is that equal to 32? If so, we're going to find the element at position I. But we know now it's not, so this if will not execute. Then we're at the end of the loop. One thing we have forgotten here, that I forgot to input here, sorry about that. We need to insert another statement here. I equals I plus 1, so that I is incremented. So we will be able to now check I will be 2 now over there, in other words, so that we will be able to check if scores 2 is equal to 32. Is it? No, it's not. So increment I again and check is score 3, and so we go on until we get to here where we will find that score 8 is the actual value. So in other words, we found it at element 8. Another example for deleting in this case. So delete the element with contents of 81 in this one-dimensional array with 20 elements. So this is a bit more difficult. Now you'll actually see, if you look at this, there's a whole lot more code that we will have to write in the end. So it basically says search for an element that has the value of 81. We'll basically search starting from here through the entire array over there, continuing over there until we eventually find element number 81. Oh, not element number 81, but the element with the value 81 in it. And it will find it at the 17th element. Okay, so now you'll see that I've created something with 17 there and there. This is simply just to indicate the values actually of I and J. Remember, those are also just variables that needs to be stored somewhere in memory. And I assume it's stored over there. So, and what needs to happen here, in fact, we're never even going to use J. So, but nonetheless, we can say while I is less than or equal to 20, first also initialize I. If scores I, so first of all it will be 1. If scores 1 is equal to 80, is that the case? No. Increment I like there and continue with the next loop. Now I is 2. Is scores 2, which is 91. Is that equal to 81? No. So we will continue until we get where I is 17. So is scores 17, which is now 81. Is that equal to 81? Yes, that is. What do we need to do? Simply exit the loop, which means we will continue over here. Now, I still has the value of 17. Check. Is I less than or equal to 19? Why not 20? Because we know we're going to delete a value here. So we will eventually only have 19 values. I is 17, so it is still less than or equal to 19. So now we say scores I, which is currently scores 17, this value over there, that gets the value of scores I plus 1. I is 17, so now I is going to be 18. So in other words, we're literally going to say scores 17 will get the value of scores 18. In other words, this value of 81 will be overwritten with 45, which is scores 19. Scores 18, sorry. And so we will continue, increase I. I is now 18. Is 18 less than or equal to 19? Yes, it is. So scores 18, which is this one here, will get the value of scores 18 plus 1, which is scores 19, this. So that will become scores 12. And so this process continues. That one over here will become 31. And the last one, the last element here, we will still need to deal with. We will now be at the end of our while loop here, but I will now have the value of 20, and we will simply have to just make I nothing there. In other words, delete scores 20. In other words, make it empty. So you can see way much more work to do when we need to delete. Similar will go for insert and so forth in here. Here's an algorithm just to show you what we sometimes also do with an array, is to try and get the average of all the elements in the array. And to do this, we can simply create a variable called sum, as in this case over here, and say initialize sum to 0 and initialize I to 1. And then we can say while I is less than or equal to n, and n might be some value that was given in terms of the number of elements. While I is less than that number of elements, sum gets the value of sum plus array I. So whatever the array is, so first I will be 1, so array 1, the first element, in other words, in the array. Then increment I and continue with the loop. I will be 2 now, so sum will get the value of sum plus array 2. And so we will continue until we are at the end of the array. And then so the sum will now have summed all the values in the array. And to get the average, we must just simply say average gets the value of sum divided by the number of elements, which will give you the average, and the average is returned. So this is just some of the basic algorithms we can use here. Also, we can get an array of strings. Very often strings, which basically mean a string is a set of characters. It's sometimes treated differently in different programming languages. For example, in the C programming language, a string is just simply treated as an array of characters. Now, it can be treated also as an array of characters in the C++ language as well as in the Java language, but we have built-in types for those. Now, just to give you an example, in memory, how we can store the string welcome to COS151 exclamation mark, it can typically be stored in memory like this. So in physical memory position number 32, we can start with an uppercase W, in position 33, lowercase e, L, com, and so forth, and spaces. This is typically how the string welcome to COS151 will be stored in memory. Technically, it's not actually a W or an E or an L that's stored there. What is stored over there? It's the ASCII value for W and the ASCII value for E. So in fact, it's actually numbers that will be stored in this memory position. And then to be able to represent it as text, the computer will know to go and consult its built-in ASCII table or ASCII character set to be able to convert whatever number is stored in there to an uppercase W and the number for E and so forth. So you can now, basically with all the examples we've seen here, you know the applications now of arrays. So you can be thinking about the operations discussed in the previous sections, and that will give you a clue of these applications. If we have a list in which a lot of insertions and deletions will take place, then basically it's not a good idea to use an array. Arrays are usually fixed in length, so we hardly ever delete or add things in arrays. There are applications where we can do that, but arrays typically are used for storing a fixed number of elements. Other kinds of data structures that are meant to grow or shrink in elements will be more useful, and we will discuss them in the last part of this chapter. And then basically that brings us to the end of this lecture. So I will discuss or take questions about this during the Monday morning lecture. Thank you very much and enjoy the rest of your day.